Hello again. This is lecture 23, chapter 6, and this lecture will be on frames. So far in chapter 6, we've talked about trusses and free and zero force members, and now we're going to talk about frames, and then we'll finish with machines. Frames and machines are fairly similar. Remember that the idea with a frame is that you have at least one multi-force member. Machine can be that way also. And when we get to machines, you'll see the difference. Fortunately, whatever you call it, the calculations and method of approach to solving is pretty much the same. So recall this picture here I showed you at the beginning of chapter 6, and this is showing how you can take a typical structure, and as in the past, we learned how we could calculate, if we knew the weight, we could calculate the tension in GD, or if we knew tension GD and the weight, we could calculate the reaction at A. Now in this case it's a pin, but if it weren't, if say it was a telephone pole stuck in concrete, then we would know it could support a moment. Anyway, the point is that in some cases you'll come across structures where you can't just solve for just by summing forces or summing moments about the outside of the external reactions. You have to actually take the item apart. And as you can see in this one, when we take apart each piece, we are left with equal and opposite forces at each at each joint. And when those are put back together again, they will cancel. So typically a method for solving is to look first and see, can I get the information I need from the external reactions? If I can't, then I go ahead and take it apart. But if you choose to take it apart first, then you can still try to solve it. It's not any hindrance. It just it might be just a different way of approaching. So let me explain that a little better because that didn't come out so good. So typically, you're going to draw a good free body diagram of the structure. And you isolate each part, and of course you want to label. And so that, I'll come back to this slide, looks something like this, where you have your frame, and here in this frame, you notice that A and B are both pins, and so they have an X and a Y component to the force. Without that X and a Y component to the force, then this structure would collapse. Now, with this structure, if we were to take it apart and actually take A and B off so that they were floating in space, they would collapse also. Now, what does that mean? If you think back to trusses, you could take a roof truss, for example, and normally we have it resting on a pin and a roller. But if you were to just rest it on the ground, the truss itself would not collapse. And so you can see this with roof trusses. Before they put them on the house, they're self-sufficient to hold themselves together. Now, with a frame, typically once you take it apart, it will fall apart. So getting back to this, another thing in a frame is you want to identify any two force members you have, because that's going to give you the direction of an unknown force. And so that can be the key between solving and not being able to solve. Also, remember that the forces are going to have their equal and opposite magnitude when they're taken apart. And that's just showing, for example, in point C, we can see that if we determine to the left that the force in C in the X direction points to the right, then we know that the force in the other component, CB, has to point to the left, and so forth. So we'll always add to 0. And in all the cases, it doesn't matter if you assume the incorrect direction to start with. Just like with trusses, you'll get a negative sign if you do that. Okay, let's look at a basic example. Now, in this one, you have a A-shaped frame, and at A you have a X and Y reaction, and at F you only have a vertical reaction. And so the question asks us to find all the components of the force A, B, and C. Now, notice that BE is a two-force member because it's pinned in two places and there's no external force. So we know that whatever the force in BE is either going to be in tension or compression, but we don't know yet. So let's go ahead and look at the drawing. So one of the things we can do is we can take it apart, but we can also start with just getting the external reactions. And that's where the frames are a little different in that so far you've kind of had a prescriptive way of approaching the problems and you generally deviate from it. With the frames, I would suggest is start by seeing if you can find the external reactions if needed, and if you can't, if you have too many knowns, then take the thing apart. Now notice that in this case we have A, we can sum the moments about A, and if we do that, we essentially have F times 3.6 is going to be equal to 18 times 4. So we get our answer for Fy to be a positive 20 kilonewtons, and therefore AY has to be a negative 20 kilonewtons because there's no other force acting. And then also we can determine or conclude that AX is negative 18 kilonewtons going to the left. So that's just basic stuff from what we know before. So now if we take the component apart, let's say we take apart CEF as I've shown. So in that case, now how did I get this? So I've kind of drawn the forces, but let's walk through the process. When I started with taking that piece off, I had a force in the X and Y direction at C. I had a 18 kilonewton force going to the right, but I didn't know what force I had going to the left. And so I've kind of got ahead of myself, but if you sum the moments about C on this one piece, the CEF, then you know that the 18 kilonewtons going to the right goes 2 meters, has a moment arm of 2 meters, and the moment arm at E has twice that. So if the moment arm is twice that, it means it's going to be half the force, right? 18 times 2 is equal to E times 4. So therefore, E equals 9 kilonewtons. Now we know it has to go to the left because otherwise the moment would be rotating, or the forces would cause it to rotate around the same direction. So we can conclude that 9 kilonewtons is to the left. Since we know that 20 kilonewtons is going up from Fy, we know that the CY reaction has to be 20 kilonewtons going down. The other thing is if we sum the forces in the X, we know that in order for CX to balance, CX plus the force at EB has to be 9 kilonewtons also. And so therefore we have a balance. So a lot of this, as you can see, is the math itself is very simple. You can do it in your head. It's just a matter of seeing what is actually going on. Now, if we look at the whole component, this is what we get. We know that 20 kilonewtons is going down, and we know that C is going 9 kilonewtons to the left, 9 kilonewtons to the left. Therefore, when we look at our ABC component, we know that that has to be the opposite. It has to be 9 kilonewtons going to the right, 9 kilonewtons going to the right, because AX is 18 kilonewtons going to the left. And we know that AY was negative 20, so therefore CY has to be positive 20. But we also knew that because the C's have to be equal and opposite. So everything checks out on this frame and all the forces fall into place. So if they don't, then obviously something has gone horribly wrong. All right. So let's do another example. Now this one's a few more steps, but pretty much the same. So what I've done is I've put these examples again on the example 22 worksheet, and you can download that. If you haven't done that, I'd pause the video and download it because it'll have all the problems. So let's look at this first one here. Now we have this member ABCD, and then there's another member CEF attached to it, and ED is a two-force member. This JBE dot in the middle, don't worry about. It's for a different problem. So it doesn't mean it's meaningless for us. But you're given all the dimensions, and we know that theta, which I didn't write in here, I apologize, theta is 60 degrees. All right, so theta is 60 degrees. Now, if we solve this with theta is 60 degrees, then you may see right away that if I sum the moments about B, then I'll be able to solve for my reaction at AX. Then I'll be able to sum the forces in the X and the Y, and I'll be able to solve for BX and BY. Once I've done that, I can then take the arm apart and just look at A, B, C, D and get those forces. So you can see kind of a repeating pattern, and that's essentially what these frames are. So let's go ahead and look at that. So here's our drawing. Again, BX, BY, AX, 60 degrees. And there's our respective distances in inches. And we're trying to find A, B, C, D. So I apologize, it's a little blurry. It's, again, this thing isn't cooperating. Okay, so first thing, as I said, we're going to find the external reactions, sum the moments at B is 0. And so I'll go ahead, write that out real quick. Okay, so there it is, repeated or written out. Again, I apologize for the focus. So here we have sum of the moments about B, which is up here. And we have AX times 8 inches, counterclockwise, minus 60 times the sine of 60. So that's that force there. And that's clockwise, and that's going to be times the distance 8 up to here. And then minus the other component, which is the vertical component, cosine 60 times 20 inches, which is the total distance across. So we get AX equals 127. If we then sum, we get AX minus 60 sine 60 minus BX. That gives us a BX value of 75.0 pounds. And then we know that if you take 60 cosine 60, you get half, or 30. So 30 is the only other force. So BY is 30 also, just by inspection. So now we have the forces. So the next thing we're going to do is we have the external reactions. We're going to go ahead and draw the A, B, C, D. So take a moment to draw that and its reactions. And I'll go ahead and do that, and then we'll solve for those. Okay, so here we've drawn member A, B, C, D. So I've went ahead and labeled. So we know AX is 127.0 going that way. We know BX is 75 pounds going to the left, 30 pounds going up. So our unknowns are CY, CX, and then DE. Now DE, again, is a force member. It could be going up or it could be going down. I don't know. I'm going to assume it's going down in this case in compression based on what's going on with the rest of the truss. I'm sorry, of the frame, but I could be proven wrong. So as you can see, if we want to solve, if we take a moment about C, we eliminate 2 of our unknowns, and that will allow us to solve for DE. Once we have DE, then we can just sum forces to solve for that. And that's pretty much it with all these frames. There's variations in geometry in that, but there's not really too many tricks. I do recall that probably 3 years ago we had a final, and if you didn't, in one of the frames in the final required 9 equations, 9 unknowns, and it also required a very good understanding of 2 force members. They seem obvious, but sometimes in this case they weren't. So I won't be throwing anything crazy like that at you on the final, so rest assured. But nonetheless, you should still understand this. So let's go ahead and solve. So if we sum our moments about C to 0, then we know that AX times 8, I'll just put it in the variable since we know the value, minus BY times 4 plus DE times 12. And actually, since it's going down, I apologize, it should be minus. that'll equal 0. So we have 127 times 8 minus 30 times 4 and minus DE times 12 equals 0. And so that's a lot bigger number than that. Makes sense that'd be negative. So DE is equal to about 74.7 pounds. Doesn't come out quite to exactly 75, so 74.7. It doesn't have nice answers because the original problem had the angle up here of, I think, 0 or 90 degrees, and I chose 60. So anyway, so we have DE, so now we just need to sum the forces, and I think you guys can do that. So if we sum the forces, knowing that DE is down, then we can calculate that CY is going to give us 44.7, and CX will give us 52.0. And that's that. So we have those values. And in that case, the directions that also, the other thing is the directions I drew them in are in that. If they weren't, then I would have indicated here. Sometimes, or I should say, is if you want to make sure that it's understood, sometimes you just draw it like that or like that. Then there's no question which direction they're going in. But since it followed a free body diagram, we're okay. So hopefully that makes sense. Let's go ahead, go back to our PowerPoint and look at another problem. Now I apologize, this picture isn't the best. Now, in this case, we have a problem where you have two reactions, A and C, and both are X and Y reactions, so there's no roller here. So we can't start the problem by summing the moments about a point. So if we sum the moments about A, we're going to have CY and CX as unknowns and no way to solve it. If we sum the moments at C, same thing. So this is an example of where you really can't start by finding the external reactions. You have to actually start by taking the thing apart. So let's go ahead and do that. So here's our diagram. Now we know that our 150-pound force, there's 3 here and 2 there, and this is in feet. So 3 pounds, 2 pounds. This radius is 2 also, so it's a 2-foot radius. Okay, and so we have everything. So now if we look at this, if we were to take this apart, then this is what we'd have. We have AX, AY, BX, BY. So we can see now that if we sum the moments about one point, A, for example, then we can solve for BY. So if we do that, then we know that we have BY times 5 minus 150 times 3. Therefore, BY gives us 90 pounds. So because BY is 90, 150 is there, that means AY has to be 60. Okay, so we know that, but AX and BX are still, all we can know is that they're equal and opposite. And even that, we don't know necessarily that they point inward like that. We still have to establish that. So now we have to go and look at the other piece. So since we can't do any more with that. Now remember, we're trying to find AYAX and CYCX. So if we go ahead, draw our quarter circle. So in that case, there's our center roughly. Now we know that we have 100, and that's at a 45-degree angle because it's going to the center. We know that BY equals 90. So I wrote that kind of close. That's there. But notice how BY is 90 because we knew BY was going up, had to be 90 there, so therefore it has to be opposite going down there. So we know that for a fact. We're going to assume BX is going this way, but we still don't know. So question mark there. And then we have, we'll draw CX going that way to the left. That's better. And CY going up. I'm going to adjust the shape. Okay, so here we have this. So we know that this point here, we'll call that O, is the center. And the nice thing with that is if we sum a moment about that point, it gets rid of BY and CX, and it leaves us with just CY and BX, doesn't it? Now, one of the things that we can conclude in this, that, well, what we can conclude is that I skipped a step, and I apologize for that. So one of the things that I should have done, and go back here, is it's true that we found this is 90 pounds, but if we come back knowing that AY is 60 here, that means we can solve for CY, can't we? Because we know 60, 150, 100 all has to be balanced by this. So if we say AY plus CY minus 150 minus 100 times square root of 2 over 2, which is just cosine or sine of 45, then that equals 0. So if we substitute in for AY our 60 here, then we can solve and get CY equal to 167. All right, good. So that's why when I looked at this, I thought, wait, we have two notes. So you know, this is 160.7. So therefore, and you can probably see this yourself, if we know CY is pointing up at 160.7, and if this has a radius of 2 and a radius of 2 and everything drops out, that means BX has to have the same value as this, doesn't it, in order for that to balance, because it's 160 times 2 equals or minus BX times 2. So essentially the same force. And we've proven that BX has to point to the right on this component in order to balance, because we know this is going up. Therefore, we know BX is going to the left and AX is going to the right. So we've established that. So we know CX now. We know that BX equals 160.7. Now, if we know that, though, don't we know what CX is? Because we know that that's going to be 160.7. And then if we sum the forces in the X, then we have 160.7 minus CX minus, and again, it's 100 times square root of 2 over 2, same in both X and Y, all equals 0. And so if we do that, we get CX equals 90 pounds. So we have CY, we have CX is 90 pounds. Now we've established that BX is 160.7. But if we go up here, we know that AX and BX are equal. So therefore, AX is 160.7. Okay? So it all kind of fell together. So if we write it down here, we know that AX equals 160.7 going that way, pounds, proper sig figs. Do as I say, not as I do. Just kidding. And then we know that AY equals 60.0 pounds going up. And then we know that CX equals 90 pounds going to the left, and CY equals 160.7 pounds going up. All right. And there you have it. So that's that problem. Hopefully that makes sense. But again, this is a type where if you, again, and you'll see these sometimes where you have reaction here, reaction there. And so looking at it as a whole, and actually if we had given you this problem in chapter 4, you probably would have questioned your head and said, well, you can't solve it because we hadn't talked about taking it apart yet. But again, you can always do that because you know the individual components have to be in equilibrium. All right. Let's go back. All right, so there are a couple examples on here. Now, in this example, we have a structure. And so here you have a 3-foot diameter pipe, sewage pipe, supported every 16 feet by a small frame ACE. So imagine the pipe is coming out of the screen towards you, and the pipe weighs 500 pounds per foot. So you want to calculate all the forces acting on CDE, or that one member. And so the pipe is going to have a weight of 500 times 16, right? So 8,000 pounds essentially is the force of gravity acting on it. So if we look at this, and then when we walk through it, here's our structure. And go ahead and show you this. So start off. My angle wasn't that great, but so I know that the distance here is 8, and that's 6. So this is a 3, 4, 5 triangle, all right, because of that. Now this sits here like this. So let's just focus on that for a second. We know that if for the pipe, the reaction on the pipe itself is going to be B pushing to the right. We know that W is going to be down, that's weight. And we know that D is going to be pushing in up at an angle. Now, because this line here is a 3, 4, 5 triangle, the perpendicular line to it is going to switch. So it's going to be a 4, 3 triangle instead of a 3, 4. So this is the same as when you take the reciprocal of, if you have a slope of a number and you want to know what's the line perpendicular to that number, you take the reciprocal of the slope, right? So if the slope's 3/4, the slope of that perpendicular line to that slope is -4/3. That's what we have here. We're aiming, the slope here is a positive 3/4, but our perpendicular line is a -4/3. So hopefully that makes sense. So if we do that, then we can form a forced triangle, 3, 4, 5 triangle, where we know that the weight side is down, the right side, the 4 side is going that way, and the 5 side is going that way. Okay, and that's how we got our structure. Okay, and so weight ends up, and actually, I apologize, this. Sorry about that. So because it's a 2-to-1 ratio, so 4:3. So that means that B is 6. So B is 6 kips, and the weight, of course, is 8 kips. We know that, and D is going to be 10 kips, and that's just by the triangle. All right. Now the next step in this problem is we know now that we want CDE. And really what we want to know is what is pushing down on CDE. We want to know the reaction at C, and we want to know what force is pushing down here. And then we can solve for it. But first thing we need to figure out is what is the distance between C and D? And so this is kind of a tricky problem because you have to go back and look at it. Trig that accounts for it. But if you think about, here's our line BC, here's our line CD. And in this case, what have we done? We have the pipe sitting there. All right, so we know the distance from B to C is 3. We're given that in the problem. So then we know that the radius of this is 1.5, so the diameter is 3. So let's look at this. If I draw CD, a line that's tangent to that, so like an ice cream cone, one of the things I know is that this is a 3, 4, 5 triangle, and then I know that this is a 4, 3 triangle, right, because they're reciprocal. So I know that if I'm trying to measure this distance from here to here, right, that's going to be the same distance as from here to this point here. So hopefully you agree with me now. So from there to there, it's the same as from there to there. Well, I know that the distance from here to here is r. I know the distance from here to here is going to be 3/5 r. So this little corner here is 3/5. And then I know that this is going to be 4/5 CD. Okay, so you can see kind of what I've done. I've taken the distance BO, that vector, plus 3/5 of OD, because if I were to go from here to here, that would be radius, but that distance from there to there is only 3/5 of it, and that equals 4/5 of CD, which is this. So if I solve, because of plugging radius, I end up with 2r equals CD, CD equals 3 feet. And actually, this is an old geometric proof that if you take a point from a distance and you draw two tangents, they should be equal. I don't remember exactly, but it looks vaguely familiar. Hopefully, I'm not wrong. But anyway, we've proven it out there, but that's how you do it. So that's kind of the big part of this problem that we need, because we need to know where this intersects here. So we'll hold that thought for a moment. And let's look at our point. So we know if we go back to A and C, we know that we're going to have CX and we'll have CY. So we have C sub X, CY, we have an A up here. Now we don't care about A. So what we're going to do is we're going to sum the moments about A and try to figure out what the reaction is down here at C. So if we do that, we know sum moments at A, 0, sorry about that, focus, we have -6, because it's a clockwise moment, times 6. So this distance is 6, this distance is 3. And then that's going to be plus C sub X times 9, 0. So 36, 9, C sub X is 4. All right, so it's going to be 4 kips. So we had B, which we calculated up here to be 6, right, because it was that side, and now we know that. Okay, so next step is to look at the actual remember CDE. So now here's CDE, and so notice that if I draw CDE, I know that because I proved in the other one that 4 is pointing to the right, that therefore, I'm sorry, at C, I knew that 4 kips pointed to the right on the other member, therefore the 4 kips has to point to the left on this member. And then CY, I don't know which direction it is yet. I'm still trying to determine that. And I know this force right here is the force of D where it contacted. So I know that that's going to be 10 kips. All right. And then since I determined that this distance from C to D was 3 feet, and I know this whole thing is 10, I know that's 7. That's why I need it. So now I can do my moment. So if I take my moment dot E, that'll allow me to find CY. Once I know CY, I can see the forces of that. And that's it. So let's go ahead and look at it. Sum moments dot E, get 4 kips times 6 feet. That's 10 kips times 7, minus CY times 8. And we get CY to be 5.75, pointing us. Sum the forces in the X, we get -4 plus 3/5 kips, because that's still the 3, 4, 5 triangle, plus EX. EX is -2, or 2 kips going to the left. Sum the forces in the Y, 5.75, which was CY, minus the 4/5, 10 kips, plus EY. EY is 2.25. So notice that once you have this part, silliness here, that you're done. And so again, I know this is a little monotonous, and I'm trying to make it as interesting as possible. So I guess I can do a little shadow. Sorry. But it's getting late in the quarter. So here we have this, you have that, and you viewed it. So hopefully that makes sense. All right. So I hope that helped you with frames. I do have one more example I'm going to go through quickly, not to torture you. Again, I'm not really torturing you because you're not a captive audience. You can pause this video at any time. And but I would like to show you this one last. So in this one, we're trying to, again, this is a lot like the one we just did a couple problems ago, or actually the first problem. So you have this structure, and you're trying to find all the forces in member A, B, D. Now, so I'll kind of give you an outline of how we do this, and then we'll go ahead. So in ABD, you're, again, because you have one force as a reaction, only in one direction, a roll-up, you're able to find AX and AY. Once you have AX and AY, then we're going to take this thing apart. Then we'll have, but we have to find B and we have to find D. Now B is not, this is not a two-force member just because it connects between B and C, because it has externally applied forces to it. So you can't just draw a line between B and C and say that's good. So we don't know the direction of B, we don't know that it's X and Y, we don't know the direction of D, it's X and Y. So we can't really do much with ABD as it is. So we're going to have to then take it apart again. You can maybe see how if we take that apart, CDE, then we will be able to sum the modes about C to get part of D, and then come back and solve for the rest of it. So let's do that, and I'm trying to make it as painless as possible. Okay. So here's that structure. There's our distances, 6, 9, 12, 12. Okay. Now there's our A reaction, there's our external D. So if I sum the moments about A, 0, I know you guys can see that. So what I'm going to tell you then is that results in EX being equal to 1110 pounds. All right, so that's that force there, EX. So therefore, AX equals negative 110 pounds, right? So AX is going that way, so 10. And then if we look at the rest of it, we know that this plus this is 600, therefore this has to be going up, and that's 600. Okay, so just visually we can see all that. So now we'll go ahead and, as I said, is we have this piece here. Go ahead, draw it real quickly. Okay, so here's our structure. So first off, here's A, B, and D. So here's my forces I've labeled. There's B. Now I put this 1 to 3 here, and that's because this is 6 and that's 18. So it's a 1 to 3 ratio, and we'll need that later. And then we don't know D, we don't know B, X and Y components. So we come down and we look at this component here, CDE. We do that, notice that we can solve for dx right here because something was about C that gets rid of these variables. Now you don't really need to really do anything because we know that this distance is 12, this distance is 12. So if this is 110 times 24, and this is dx times 12, basically it's half. So that means in order for it to hold this at twice the distance, it's going to be have twice the force. So this, we can say, is 2220, can't we, in order for it to be balanced. So if that's pointing that way, then we are correct up here that this is pointing that way. So establish that that's going to the left, otherwise it will be balanced. And then we don't care anything more about this. So then we come back here and we can say, well, 2220, and we know that therefore this has to also be 1110 EX, right? And the other thing is now the only thing is we have two of these. Now, you'll notice that if I sum the moments about B, that's where this 1 to 3 came in. If I have 600 times 1 and dy times 3, then that's pretty easy to see that that's only pounds. And so therefore, if that's 600 and 200 established going up, dy has to be 800 going down. All right. So your answer, let's say you were doing this in final, you just want to make sure that your answer has everything. Has AX equals 1110 pound, AY 600 pounds, BX is 1110 pounds, BY equals 800 pounds, arrow going down or negative, whichever you prefer. If you want, you can put arrows here too. There's no question. And then dx, and actually, what was I thinking? This is going the other way. Someone reached back in time and told me to fix that. If I saw it, go, wait, that's wrong. And I heard you a few days before when I was recording this. I changed it. So here we have 110 going that way, 800 going down, and dx, of course, is 2 or 2.22 times 10 to the third for proper sig figs. And that's, of course, going to, right? And then lastly, we have dy equals 200 pounds. All right. So that's that. So those were 4, hopefully not too nauseating examples. But the idea, again, is just don't overcomplicate them. If you can solve them, if you can get as much information as you can without taking it apart, do that. And then once you have garnered that, take it apart, solve what you need. And, okay, so that concludes lecture 23. Lecture 24 all introduced machines, and then we'll move on to friction. So thank you for listening.